Now let's take a look at example number 3. I want to find the area enclosed by the curves y equals x minus 1 and y squared is equal to 2x plus 6. Now what I might see here right away is that the second curve is going to be a little bit awkward to graph. I can go ahead and think about this in two different ways. I could think about saying that this is going to be plus or minus the square root of 2x plus 6. That is, this is a sideways parabola with like a top half and a bottom half. Or I can imagine rewriting this in an x equals form, which I believe if I do that, and you can double check me on this, I believe I would end up with a 1/2 y squared minus 3 from subtracting the 6 and then dividing everything by 2. Now regardless of which way I think about this second curve, I should be able to go ahead and provide again a rough sketch of what my region looks like. So I'll start by graphing this sideways parabola. I like this x equals form because it shows me that this is a parabola that opens towards positive x's. I have a positive leading coefficient here, but that it's been shifted back 3 units. So like over here at -3 is where my parabola is going to start, and then I know it just opens up to the side kind of like this. I don't necessarily have to draw my picture perfectly to scale. In the same way, I know that my line y equals x minus 1, although it starts down here, I'll just kind of eyeball the rest of what's going on with this curve. And so let's suppose I get something that looks like this. The region then that's being bounded by these curves would be this region right here. And I'm going to go ahead and start to think about how I would begin to maybe work with this region to find its area. Well, like we've done in the past several videos, I'll start by drawing in some different rectangles that I have. And I'll notice something kind of interesting taking place here. First off, my rectangles are certainly not all the same length. They have different lengths or different heights. But if I wanted to come up with a formula that would be able to tell me those heights, I would need to determine what function's on top, which is, I guess, my parabola function, but then what function's on bottom. Now, this is kind of strange because if I look at what functions on bottom, I'll see that not every red line has the same bottom function. These red lines over here on the right have a bottom side that's on this line. But on the left side, the bottom of my rectangles is occurring on the other half of this sideways parabola. So in general, this becomes a little bit tricky to work with. So I can say here, this is tricky to do with vertical rectangles since y squared equals 2x plus 6 is both the top and bottom function, or I guess I shouldn't use the word function here since this doesn't pass vertical line test, but I could say both the top and bottom curve for some rectangles. So what we're seeing here is that while it might be easy to describe some of the heights of some of these rectangles, it becomes a little bit more difficult over here on the side. Now, I could possibly use this square root form to try to help with this by treating the top half as that positive square root and this bottom half as a negative square root. And so while this problem is still able to be done with vertical rectangles, it is a little bit trickier. I have to understand splitting apart this sideways parabola into two pieces. So instead, we're going to try to go ahead and tackle this problem using a new approach. So I'll say, we will try a new approach. And we'll see that from time to time, new approaches may be necessary to help make a problem doable, or maybe just to make it much simpler to actually try to work with. So let's take a look here at the next page. We're going to talk about the idea of integrating with respect to y as opposed to integrating with respect to x. Now typically when we say that we're integrating with respect to x, we're thinking of like having a dx problem where I have widths of rectangles that were going in like a horizontal direction, and so my rectangles were shaped vertically, kind of like the pictures up here. However, when we say that we're going to be dealing with a respect to y integral, we're going to imagine just changing the orientations of the rectangles, kind of like I have here. Imagine I have a space that exists between two functions. However, you'll note that my functions here are x equals functions. They're x equals stuff with y, and x equals more stuff with y. And I have an area that's starting at a y value of c and goes up to a y value of d. In the definition down below, I change these values to a and b, but it's the same base idea. But notice that my rectangle here is horizontal, and so I'm going to have a width that's vertical, and so it's a delta y. It's a change in a y coordinate if I divvy up this here, this c to d interval. I'm moving in the y direction. And then I have a length of my rectangle, which would be pretty easy to spot. Notice that in order to do this, I'd have to figure out what x coordinate the right side of my rectangle is on, what x coordinate the left side of my rectangle is on, and if I took the bigger x coordinate and subtracted the smaller one, I would get the total length of that rectangle. And if I have the length and I can multiply by the delta y, which would be the height, again, I'll be able to form the area of that rectangle. Add a bunch of those up and slap a limit on it, and I'm right back to a nice integral. So let's take a look at what we have down here. The area of a region bounded by the curves x equals a function with y, and x equals some formula with y for g there, and the lines y equals a and b, or in the pictures up above I have c and d, as long as again I have continuous functions, and f is a bigger function than g. Notice that means it produces a bigger x coordinate, so f's got to be on the right side where bigger x's are. Then I can see here that this is going to help me measure, oops, let me fix that. This is going to help me measure the length of my rectangles, and this part back here is going to help me measure the height, but ultimately I'm still getting the area of my rectangles. And then I just have to state where my rectangles start and stop, which in this case is C up to D, or as I stated down here, I could imagine that it's still going from A to B, but now in a vertical direction. So I'm going to see how we can try to apply that to example number 3, which was the example we started looking at the beginning of this video. So I'm going to really quickly try to just re-sketch out what our picture looked like. We had something kind of like this, and then we had some sort of line that went like this, and we had our blue space. And while we saw when we looked at this example previously that vertical rectangles kind of changed their top sides or bottom sides, and it made it a little bit difficult, notice what happens if I put horizontal rectangles in here. If I put in horizontal rectangles and I need to figure out how long they are, I'll just need to know what function forms their right side and which one forms their left side. And I would be curious if this is always the same for all the rectangles. I'll notice that the right edge is always on my line function, and the left edge of all these rectangles is on this sideways parabola. This means that I can probably tackle this here with only one integral, as opposed to have to using multiple integrals in the dx direction. So to tackle this, we can go ahead and start by thinking about all the different pieces of information we would need to fill in this above formula. Well, one of the first things we need is to probably take our functions and solve them to say x equals. So I'll say here, we will rewrite our functions. So let's do this one at a time. I have y equals x minus 1, and I can change that into an x equals formula. That's pretty easy. That would be y plus 1. So this curve over here is x equals y plus 1. Notice that's my bigger curve because it forms the right edge. I also have my y squared equals 2x plus 6. And at the start of this video, we saw that we could rewrite that as x equals 1/2 y squared minus 3. So that's what I have over here. X equals 1/2 y squared minus 3. Now, it's then pretty easy to see that to get the length, I would need to take my y plus 1 and subtract from it my 1/2 y squared minus 3. That is, for any y value that I'm sitting at, if I know that y coordinate, I just go ahead and I grab the x coordinate on the right, calculated by this formula, and subtract the x coordinate on the left, calculated by this formula. I also have dy, which is pretty easy. The last thing I would need is just my bounds. I would need to know how high and how low do these rectangles go. And what I'll see is that means that I'm going to be kind of looking for these green points of intersection, because that's how low or how high up I can actually move my, or draw in my little horizontal red rectangles. So I'll now try to find points of intersection. So I'll say we need points of intersection, and this is also really easy to find. I can go ahead and just take the two equations that I had and set them equal to each other. So I know that y plus 1 would have to be equal to 1/2 y squared minus 3. Or of course, you could go ahead and in the original forms, you could also just do a substitution and say that x minus 1 squared, or x minus 1 can be subbed in for y, and that creates this equation. Now, either of these is going to be able to be tackled in a very similar way. I'll go ahead and just focus on maybe the first one since it has x's. But working on this one here, let's see, I'm going to get an x squared minus 2x plus 1 equals a 2x plus 6. That's going to give me an x squared minus a 4x minus a 5 is equal to 0. From here, I know that's going to be x, let's see, minus a 5 and x plus a 1. And so I'm going to arrive at x could be equal to 5, or x could be equal to negative 1. In fact, that seems to jive with the picture. I have an x value of negative 1 above my green, and an x value of 5 that's occurring below this other green point. Of course, what we really need are the y coordinates that are associated with those. But of course, if I have the x, I can easily find the y. If x is equal to a value of 5, then certainly my y is equal to a value of 4. I'm just using my linear function to determine that. And if x is equal to a value of negative 1, then y is equal to a value of negative 2. And so I can see here I have my bounds from negative 2 up to 4. That is, those green points of intersection had the coordinates of 5, 4 and negative 1, negative 2. So with all of this information, it's now unbelievably simple to set up my integral. The total area that I'm looking for can now be found by integrating my y plus 1 function minus my 1/2 y squared minus 3 function, multiply that by my dy, and then my bounds, remember, state how low and how high my red lines can go, which in this case they can go from negative 2 all the way up to 4. So this here would be an integral that actually represents that area. Now again, I'm going to leave it up to you to actually try to evaluate this, but this should be pretty easy because notice you just have a little polynomial here and can integrate that hopefully no problem. If you do attempt to integrate that, your final answer that you should be able to arrive at is 18. So go ahead and try to work through that problem on your own. And of course, let me know if you have any questions.